Hi there, welcome back. So now let's move to transition to turbulence. So let's address two tutorials. Okay, so we're going to do the flat plate and three-element airflow. So first, let's work on the flat plate. So let me show you what we're going to do. So this is a traditional flat plate, but now we're going to consider transition to turbulence. Okay, we're not going to assume that we have the onset of the turbulence immediately when the flow reach here, the edge of the flat plate. Now we're going to see the critical, to measure this critical length. Okay, so this is another classical case in validation, specifically related to the transition to turbulence. And just to remind you, transition to turbulence is very difficult, okay, very tricky to capture, very elusive, and requires very fine meshes. So here you have a few references, and basically this is the first case that we have. Okay, we have this mesh. Look at that, is very fine, okay, towards the normal to the wall. Okay, so we have the flow coming here, this is the wall, and then reaching this edge, and we're going to have the development. So basically we're going to see something like this. Will be a laminar region, a transition region, and then the fully turbulent region. So by looking after running a solution, okay, this solution, by the way, are economical. Even the mesh is very fine. It is economical. We're going to run a steady. Okay, so we have pressure contours and velocity magnitude contours. So nothing much to see here. But now let's take a look at the, for instance, here are the turbulent kinetic energy. Okay, and look at it here, making the reference that the flat plate start here, and see that here you see all these regions that we don't see any turbulent kinetic energy, and then here you have the development. So this is already indication, the fingerprint of transition to turbulence. Okay. And if we move another slide, go forward, now we have the eddy viscosity ratio, and this is a very important quantity. Probably people ignore this one, but this one is telling a lot about what you are doing, but also it's a good guideline to check if you have a good mesh. But basically remember that we have seen now when we look at the budget of turbulent kinetic energy that turbulent kinetic energy peaks in the buffer layer, in the boundary layer. So see that this is an indication where you have the maximum. It means that you're in the boundary layer. Okay, so this can be a very good guideline to do your mesh, to have a nice stretching. Okay, see here 0. Okay, see that this is a laminar, and then it changes. It means that it goes turbulent. And then we are going to look at this quantity, the intermittency. Means, okay, basically this means that 0 we have laminar flow, and then 1 you have fully turbulent flow. So see that here at the beginning of the flat plate we have a rather thick region now with laminar flow, and then okay, we zoom out and see that it becomes thinner. Indication now that we have the turbulent boundary layer there. Okay, and then we're going to do, so these are the colors. Then we're going to do the traditional sampling, and we're going to sample in 2 locations. One location in the laminar region and one location in the fully turbulent region. And we're going to see this normalized velocity profile that I hope we are very used at this point. And this is what we're going to see. So look at that. If we plot in the sample location 2, here in the turbulent region, see that we have this. So see that pretty much we have this blending. Okay, so see that we go from laminar, then we have the buffer layer, and then it will blend toward the the turbulent region, the log region. Okay, so see that here we have a very short region. Okay, so as you go further in the flat plate, probably you will get something wider, but we're getting that behavior that we have seen, we are getting used, and something that we know from the theory. Instead, if we look at the laminar region, see what we have, the traditional behavior. Instead of doing the blending, see that it's just following the laminar profile. Okay, and then, well, remember when you see this one, means that you are now in the effects of the fringe strain. Okay, you are outside of the effect of the velocity gradients and that stuff at the walls. Okay, so this is a traditional behavior. And remember, this behavior also, you can have it, for instance, when you have flow separation, you are going to have a similar behavior or something like this. But remember, in flow separation, not necessarily will translate in lower drag, because you have the forward drag. Here, this is skin friction, so this is translating okay, directly into lower skin friction drag because we don't have any separation, okay. And then also we have the validation data, okay, is the skin friction at the flat plate, and see here we have our experimental values, numerical values, and see here clearly we can see now the transition. So see that the beginning we have laminar following this laminar behavior, and then we have here the transition is doing the switching and then becoming fully turbulent. What is interesting that then is you run this case using a fully turbulent model. We're going to see that one. You will see that this line, the turbulent, this numerical line will be something like this, fully turbulent. And as you use a laminar model, it will just follow this one, okay? So this is a problem with these cases. This is extremely difficult to capture. You need very well calibrated models to do this, and also very fine meshes, in particular normal to the wall, but also in the stream-wise and spans-wise dimensions. Okay, so that's all for the introduction of this case. So as you download the cases, you have here the Fluent files and the Fluent meshes and setting, and also validation data. You should get something like this, okay? So you should have the Fluent case, okay, this is ready to run. You have the validation data, the usual data that we're putting for flat plates, okay, but for the velocity profile, and then you have clean meshes, okay. So that's all for the moment, okay. Thank you for your attention, and see you in the next video. Bye.